Hi, this lesson is about solving exponential and logarithmic equations. So we'll start with exponential equations. An exponential equation is one in which the exponent is the variable and the base is some positive number. And one way to solve an exponential equation is to take the logarithm of each side of the equation. You can use either the common logarithm, which is log, the one with the base 10, or a natural logarithm, which is ln. Either one will work. So this is an example of that. I want to solve e to the negative x equal to 17.54, and we're going to round our answer to the hundredths place, which is the second decimal place to the right of the decimal. So I'm going to take the natural log of both sides of this equation. Natural log is the best choice here. Although they both work, the reason why natural log is the best choice here is because the natural log and e to the x are inverse functions of each other. So that unique relationship allows you to simplify things more easily. So I take the ln of both sides of the equation. You will need a calculator to complete this problem. On the next step, I use the logarithmic laws and put this negative x in front. So this becomes negative x ln of e. Remember, that's what we call the power law. But then remember, ln of e by definition is equal to 1, and that's, again, because the base of the natural logarithm is e, and e to the first power equals e. So your answer for a logarithm is the exponent. And then at this point, I would plug this into a calculator. Round it to the hundredths place leaves me with negative x equal to 2.06. But then you need this to be x, not just negative x. So you can multiply or divide both sides by negative 1. And so you get that x is negative 2.86. For the next one, we're going to apply a similar technique, but I'm going to use a common log, in example 2. In this case, when I want to solve 5 to the x minus 1 equal to 2, you could take the common log of both sides, or you could take the natural log of both sides. Really wouldn't make a difference. You just want to use a logarithm that you have in your calculator, because you do need technology to solve this. So if you take the log of both sides, that's what it looks like. But then I can move the exponent in front of the logarithm. Again, this is power law. And so I have x minus 1 times the log of 5 equals the log of 2. I distributed the log of 5 across the x minus 1. Log of 5 is just a number. So I'm left with x log of 5 minus log of 5 equals the log of 2. Then I added the log of 5 over to the right side, and I divided by this log of 5 so that my x would be alone. So x is equal to the log of 2 plus the log of 5 in parentheses divided by the log of 5. At this point, you could plug this directly into a calculator the way you see it. I simplified it a little bit more. I used my product law because I know that the sum of two logarithms with the same base could be written as the log of the product of 2 and 5. And the log of 2 times 5 is the log of 10. So the log of 10 is really equal to 1. So if you enter 1 over the log of 5, you would get that this is about 1.431. I rounded to the thousandths place in this case. Make sure that when you're doing a problem, whether it's using technology, a homework platform, or directions on a paper document, that you're reading the directions in terms of where to round off your answer. You could have just entered this as well, and you would have gotten the same answer. So the next one, again, we're going to apply a similar technique. I have 15.6 to the x plus 2 equals 23 to the x. It's a little bit more complicated because I have x's on both sides of the equation. And again, I'm going to use logarithms to help me move things around and so that I can solve for x. So again, I used a common log. You could just as easily have taken the natural log of both sides. So when I take the log of the left side and the log of the right side, I again can apply my power law and put the exponent in front of the logarithm, which is what you see on this line. X plus 2 log of 15.6 equals x times the log of 23. On the left side, I distributed the log of I distributed the log of 15.6. This number got distributed across the x plus 2. So I'm left with x times the log of 15.6 plus 2 times the log of 15.6 equals x times the log of 23. So I need to get the two terms with x's on the same side. So what I did was I subtracted this expression over to the left, so you get the next line, x log of 15.6 minus x times the log of 23. And then I moved this number over to the right to get it separate from the expression with x. And so I end up with negative 2 log of 15.6 on the right side. So here I factored out an x, which leaves me with x times the log of 15.6 minus the log of 23 equals, and I already plugged this into a calculator. I definitely gave myself more decimal places than what my final answer is going to get rounded to. And you always want to do that. Go a decimal or two further out. I went 5 out. So this is about negative 2.38625. And this is a number that you can use your calculator to compute, and that's actually equal to negative 0.168603. I divided by that number so that I can get x by itself on the left side. And when I divide those two negative numbers, these two, you end up with 14.2 when you round to the tenths place. Okay, so that's one technique, which is to take either the common log or the natural log of both sides of the equation. Another approach to solving exponential equations is to rewrite both sides of the equal sign in terms of the same base. Not all equations can be done that way. We definitely could not have done any of these with this second technique, but some can. And so if you can rewrite both sides of the equation in terms of the same base, then you can ignore the bases and just solve what's left in the exponents. So if you end up with an equation that looks like this, b to the x equals b to the y, then you can ignore the bases and just solve whatever's left there. Then x must equal y, and you'd be able to solve for whatever your variable is. So this is an example of that second technique. I'm going to apply this technique to this one. I have 2 to the x plus 1 equals 16. Unlike the previous examples, I can rewrite the 16 in terms of a base of 2 because 16 is 2 to the 4th power. I would not have been able to do that here. I would not have been able to write the 15.6 with a base of 23, and I would not have been able to rewrite the 23 with a base of 15.6. So this technique only works in very specific situations. So now in this example 4, my left side and right side of the equation have the same base. So I can then ignore the base of 2 and just solve the exponents. That means that x plus 1 must equal 4. And this is a simple equation to solve. Just subtract 1 from both sides and you get that your solution is 3. This is very easy to check. Just plug in 3 where the x is. If the left side equals the right side, then you know that you have done this correctly. So I get 2 to the 3 plus 1 equals 16. 2 to the 3 plus 1 is 2 to the 4th, and 2 multiplied 4 times is 16. The left side and the right side are equal, so x equal to 3 is a good solution. I'm going to be able to apply this same technique to number 5. I have 5 to the x squared equals 25 to the second. So 25 could definitely be rewritten with a base of 5. But don't forget I'm squaring this. So this will be 5 squared squared. And when you have an exponential expression raised to another power, you simplify that by just multiplying the two exponents. So I get 5 to the x squared equals 5 to the fourth. At this point, you can ignore this base of 5. You can just ignore them and just solve what's left. That must mean that x squared equals 4. And if you take the square root of both sides of this equation, you get two answers, positive 2 and negative 2. And if you were to plug either one into this, the left side would equal the right side. So in this case, you end up with two solutions. Okay, number 6 is going to be handled in a similar way, although it might not be quite as obvious at first how to do this. I have to rewrite the 1 with a base of 3. And the way you do that is that I'm going to write the 1 as 3 to the 0 power, because any base raised to the 0 power is equal to 1. And now I have the same scenario. Same base on both sides. I can ignore the bases and just solve 2x equal to 0. So in order to solve 2x equal to 0, you just add 1 and divide by 2. In this case, you get that my solution is x equal to 1/2. Okay, so those were a few examples of exponential equations. Now we're going to talk about logarithmic equations, and there, again, will be more than one way to handle this. One thing to consider is that sometimes you'll be able to use your logarithmic laws or properties in order to condense one or both sides of an equation with multiple logarithms into just a single logarithm. And when that occurs, if you can get a single logarithm on one side equal to another logarithmic expression on the other side with the same base, they have to have the same base. Wouldn't matter what the base is, but they have to be the same. Then you can ignore the logarithms and just solve for what's left. So then I would solve x equal to y. So that's one approach, which is very similar to the approach I took on these problems, where you wanted the same base on both sides and then ignore the base and just solve for the exponents. Here you're trying to get the same logarithm or single logarithm on both sides with the same base and just solve for what's the other parts. So whatever you're taking the log of. So that is a technique. Another technique is to rewrite the logarithmic equation as an exponential. And if you can do that, then you can use some of one of the techniques that I just described with exponential equations. And so as a reminder, if you have a logarithmic equation, that could get rewritten as an exponential by saying x is equal to b to the y. So you're going to be using either this as a technique or this as a technique. And it really depends on the problem. And so in example 7, I'm going to be using this one. I don't have a logarithm on this side, so I'm not going to be able to do what this is stating. I'm not going to have a logarithm with the same base on both sides. So I'm going to try to rewrite this as an exponential expression. So this goes back to an earlier lesson. I cannot convert this into an exponential expression until I get rid of that 5. And so the way I do is I'm going to do that. I'm going to divide both sides by 5. So then my logarithmic equation is log base 32 of x equals negative 3/5. Now I can apply this definition. A logarithm gets rewritten as exponential as follows. So that means that x will equal 32 to the negative 3/5 power. But this is something I can work with. A negative exponent ends up in the denominator, and when your exponent is a fraction, it could get rewritten as a radical. So 32 to the negative 3 halves is equivalent to 1 over the fifth root of 32 to the third. The fifth root of 32 is 2, but then I still have to raise it to the third power, and so my x is equal to 1/8. So we have solved the logarithmic equation by first rewriting it as an exponential equation. Okay, then for number 8, I'm going to apply this technique. And the way I'm going to do that is first I'm going to use my power law and write this as an exponent. So I get log of 2x minus 1 to the third power. This is a common log. Remember, when you don't see a base, it's a base 10, which is a common log. And this 1, well, I can write that as a logarithm. So the log of 10 is equal to 1. And that goes back to a formula or a rule that I gave you in a previous lesson, is the log base b of b equals 1. Well, that's exactly what we have here because the base is 10 and I'm taking the log of 10. So these two numbers are the same. And then I can apply this. I now have a single logarithm on each side with the same base of 10. So then I can ignore the logarithms and just solve 2x minus 1 to the third power equal to 10. In order to do that, you take the cube root of both of this equation. So I get 2x minus 1 equals the third root of 10. And then I add 1. And I get 2x equals the cube root of 10 plus 1. If you were asked for an exact answer, then at this point you would just divide it by 2, and this would be your exact answer. So if you're not told to round, assume that an exact answer is found. In this case, I rounded to the hundredths place. So if I take the cube root of 10, add 1, and divide it by 2, my x will be approximately 1.58. Okay, and this is just a reminder of what I mentioned earlier, that the log base 10 of 10 is equal to 1 because 10 to the first power equals 10. And the answer of a logarithm is the exponent. Okay, the next one has a natural logarithm in it. I have 4 times the natural log of 2x equals the natural log of e to the second. This one already has a natural log on both sides. So it makes sense to try to condense the left side as much as possible so that I can then solve for what I'm taking the log of on each side. So what I did was I made 4 the exponent of 2x. So I get the natural log of 2x to the fourth equals the natural log of e to the second. I can then ignore the logarithms because it's the same base. A natural log has a base of e, and I can just solve for 2x to the fourth equals e to the second. If I take the fourth root of both sides of this equation, the fourth root of 2x to the fourth and the fourth root of e to the second, well, that's going to give me 2x on this side. And on the right side, that's e to the second raised to the 1/4 power. 2 times a fourth is a half. So that's why I end up with 2x equals e to the 1/2. Then divide both sides by 2. E to the 1/2 is the square root of e divided by 2. This is again an exact answer. So unless you are told in your directions, so you have to read your directions carefully when you're doing a problem, to round, then always assume that an exact answer is what is expected. If you're told to round, make sure you're rounding to the correct place value. In number 10, example 10, I have the log, again, this is a common log of x, is equal to -4. Here, I decided to just go straight to just rewriting this as an exponential expression. Remember here, the base is 10. So that means that 10 to the negative fourth power, 10 to that power equals x. But I know that 10 to the negative 4 is 1 over 10 to the fourth power, which is 1 over 10,000. So we get 1 over 10,000 as an answer. Okay, here's one with multiple logarithms. So on the left side, I have 2 log base 2 of 3 minus log base 2 of x equals log base 2 of 45. I'm going to need to do some work on the left side to collapse this into one logarithm. So I use the power law to make the 2 an exponent of 3, and then I'm going to use the quotient law so that I could put this in the denominator. And so then I'll just have one logarithm. So first I squared the 3, so I get log base 2 of 9 minus log base 2 of x equals log base 2 of 45. Then I applied my quotient law on the left side, so I have log base 2 of 9 over x equals log base 2 of 45. At this point, you can ignore these two logarithms. They're not canceling out. You're not dividing by them. They are a function. But when you have the same log on each side and it's just one single log, you can ignore them and just solve for what is left. So I'm going to solve 9 over x equal to 45. If I cross multiply, I'll end up with 9 equals 45x and then divide by 45 so that the x is alone. 9 over 45 gives me an answer of 1/5. Okay, number 12 is very similar, except it's a natural log, but I need to collapse these two natural logs into a single one. And this time I'm going to use my product law. So the natural log of x plus the natural log of x plus 2 is the natural log of x times x plus 2. Then I have a single logarithm on each side. You can ignore them, ignore the logarithms, and just solve for what's left. So the equation that I'm solving is x times x plus 2 equals 3. This is a quadratic equation because if I distribute this, I'll get x squared plus 2x, and then subtract this over to the left so that my equation is set equal to 0. I then have a quadratic equation that is factorable. That factors into x plus 3 and x minus 1. If you set each factor equal to 0, you get that x is negative 3 and x is equal to 1. So the reason why a box is around the 1 and not the negative 3 is because x equal to negative 3 is not a solution since it's not in the domain of ln of x. The domain of any logarithm of any base is all positive numbers. So if you took the natural log of negative 3, try putting that into a calculator, it should give you a message that either says error. Some might be more specific and say domain error. It simply does not exist at x equal to negative 3 or any negative number. So I showed you how I checked ln of plugging in 1. So I have ln of 1, plugged it right in here, plus ln of 1 plus 2 is equal to ln of 3. ln of 1 is equal to 0. So the log of any number, the log of any base, if you're taking the log of 1, that will always be equal to 0, and that's because b to the 0 power equals 1. So this one just happens to be a log of base e, the natural log. So that's equal to 1. So I'm left with ln of 3 equals ln of 3. Left side equals the right side. It checks out. Okay. The next one is another exponential equation, which requires you to use factoring in order to solve it. So it is a little different than the ones I did earlier. I have e to the 2x minus e to the x plus 7 equals 0. I'm going to use something called a substitution in order to help us see that this is actually looks like a quadratic equation, or we could handle it just like a quadratic equation when we want to solve it. So I'm going to let u equal e to the x. So think of u as like a new variable. If I replace my e to the x's with u, e to the 2x becomes u squared minus 8u plus 7 equals 0. This now looks like a regular quadratic equation, just like this one was. And it's factorable. It factors into u minus 1 and u minus 7. So I get two solutions here, u equal to 1 and u equal to 7. But these are not the solutions for this equation. This equation is in terms of x. So I now have to use those two answers in order to convert it back to the variable in terms of x. So if u equals 1, u is e to the x, so e to the x must equal 1. And if u equals 7, then e to the x must equal 7. But then how do you solve an exponential equation? And this goes back to the very first problem I did. I'm going to take the natural log of both sides of this equation. The natural log of e to the x is just x. Remember, the natural log and e are inverse functions. So when you take a composite like that of two inverses, your answer is just x. And that is exactly what you want to solve for. And the natural log of 1, as I explained earlier, is equal to 0. So my first solution is 0. And then the second one, I did the same technique, took the natural log of both sides. The natural log of e to the x is x. The natural log of 7 is just the natural log of 7. This is, again, an exact answer. If you're not told to round, do not round. So I'm left with two answers, 0 and ln of 7. There are no restrictions to the domain when you're dealing with an exponential equation. We had restrictions here in this one because this was a logarithmic equation. So that's why the -3 just didn't work. Okay, here's another one. I have x squared 3 to the x minus 81 3 to the x equals 0. In this case, I also need to factor, but it's going to be a little bit different. I don't need to do any kind of fancy substitution here. This expression and this expression have a common factor of 3 to the x. So I'm going to factor that out. And I'm left with 3 to the x equals x squared minus 81 equal to 0. Then I set this factor equal to 0 and this factor equal to 0. Let's deal with this one first. It's the easier one. I added 81 to both sides, then I took the square root of both sides. I get two solutions, positive 9 and negative 9. But on the left side, this one doesn't quite work out. 3 to the x, even if you tried, you would not be able to solve that. So I can explain this to you in one of two ways. The first way is, remember that 3 to the x looks like this. So that means that 3 to the x will never equal 0. It would equal 0 if it crossed the x-axis, because that's when your y would equal 0. But it doesn't ever touch the x-axis. It's actually an asymptote. Another way to explain it is to use a technique that I was just talking about. If I said 3 to the x equals 0, and I take the log of both sides, well, the right side is impossible. You can't take the log of 0. That would give you an error if you tried plugging that into a calculator. 0 is not in the domain of log. So essentially, this part cannot be solved. 3 to the x is always a positive number. It's always above the x-axis. It's in quadrant 1 and in quadrant 2. So in this case, I get two solutions, positive 9 and negative 9. Okay, so that's it for that lesson. Good luck.